my papers will not say, you'll not see energy efficiency in the title, but you'll always find energy efficiency in the keywords. So what is this talk all about? So first, we'll see what is the mother of all future digital transformation. To be precise, we'll talk about big data and how and why is it different from regular data. Then what does big data mean for future technology innovation? And that is 5G. So we'll see what 5G is, where it stands. And then what are the different trends of 5G? So what's the big deal? So we'll talk about simply 4 basic trends, although they're not quite simple, but I'll try to introduce them in a very simple manner. And finally, how does energy efficiency or power efficiency fit in this grand scheme of things, where energy and power feature in this? So we'll see, okay, how from 5G, 6G is being evolved, which has energy or power efficiency as a driving force. So we'll discuss that. So big data is everywhere. You have Facebook, 1.3 billion users, 72 hours a minute of YouTube video being added, 6 billion Flickr photos, so data everywhere. Again, all this information, all these statistics are maybe 3 years old. So because they are for 2017, these days they must have exploded already. So maybe you're talking about 10 million Facebook users, and more than 1.3. So what is the takeaway? What is that we want to learn from this? What we learn is the data is growing at 50% a year. Every year, the data is increasing by 50%, which is a staggering amount. And the data is the new economic asset. So it's just like currency or gold or petroleum. So if you have data or you have key information from that data, you can control a lot of things. You can take informed decisions. So what characterizes big data? What makes big data different from other data? The answer is 4 V's. First is volume, right? What is the size of the data? So we're talking about terabytes and exabytes of data. Then the velocity, that means the data generation speed is much higher than regular data. We're talking about petabytes of data being generated every milliseconds. So you can imagine what is that volume and velocity is. Then variety, that means data in many forms. So you have multimedia, text, structured, unstructured, a lot of things, different types of data you're dealing. And finally, veracity, data in doubt. That means not all the data are equally important. So there's some uncertainty with different data. Data can be inconsistent, incomplete, not truthful. So that is something, so the technology has to take care of those scenarios as well. So our perspective about these 4 V's. So first you have more than 12 terabytes of tweets daily. That's the volume. Hundreds of different types of data, variety. 1 out of 3 data or 1 out of 3 decisions from the data can be trusted. The rest kind of all does not make sense. So you have to decide, you have to choose your battles. And then more than 5 million of trade events per second from just New York Stock Exchange. So you can imagine if you encompass all the stock exchange and how much of data we are talking about just from trade events. So staggering, really staggering numbers. And again, these numbers are from 2017 or 18, so they might be 2 years old. So maybe all this data and all these scale has already increased multifold by this time. So the old model to the new model is we are seeing a paradigm shift from the old to the new. So old was you have only certain outlets, certain media or news outlets generating all the data, and then the rest of us are consuming it. Now everybody is generating data and everybody is consuming. Like everybody is generating that through Twitter, through social media, through so many other things. Like imagine what is happening with COVID, what is happening with the current political situation in the US, with the protests and all. People are tweeting, those tweets are being retweeted, people are posting on Facebook, then there are comments. So everybody is joining in, everybody is generating data, everybody is consuming it. So the model has changed forever and we are not going back to the previous model. It's only going to get worse from here in terms of scale. So the modern digital transformation has solved the problem of data generation and collection. So that problem is kind of dealt with. So that's not a problem anymore because you have social media generating data, scientific instruments generating data, like high energy physics, particle physics, bioinformatics. We're talking about millions of terabytes of data like every day. you have mobile devices, sensor networks. Data generation is not the problem, but what the problem is what to do with that data, how to analyze that data, how to manage that, how to summarize, visualize, discover the knowledge and information in a timely manner. So that is driving the technology for tomorrow. Collection, generation part is solved. How to process that is something that we are striving towards. So for a shift in data paradigm motivates a shift in technology paradigm, and that shift is because there are a lot of different dimensions. What I want to show you this is like you have the 4G in the middle, which kind of has all these different features in different dimensions in terms of mobility, size of the data volume, and etc., and how 5G is expanding each of them, right? What is more important is energy efficiency, and that's what it is kind of relates or resonates to this audience. Energy efficiency. What we're talking about is 10% of the energy consumption from 4G. So if a device uses some amount of energy for 4G, the same device for 5G should only consume 10% of that. So that is one of the important factors. So the driving forces for 5G, not energy efficiency yet, because you have the data, you have the devices, and better user experience. Like I want better performance. I want my YouTube video to buffer quickly. I want my video qualities to be 1080p, HDTV all the time. So that is the user experience. But one of the byproducts of this 5G revolution is energy consumption, along with efficient end-to-end latency and efficiency in terms of hardware flexibility, because you're talking about different types of devices, mobile devices, TV and everything. So hardware flexibility and all, but then one of the byproducts is also energy consumption, efficient energy consumption, and that is evident from this type. So some clear trends are coming out from 5G. If this is the ground truth, what are the different trends? And then the next 4 slides will discuss these 4 trends. So first is PCs to IoTs. So previously we're talking about dedicated devices whose only job is computation. So we're talking about dedicated desktops, laptops, but now it's the world of IoTs. Connected devices. You have smart lights, smart phones, smart watches, smart everything, smart vehicles, smart flights, airports, everything is connected, right? And everything can be controlled with a simple app. Smart toaster. I don't know what a smart toaster does, but it's supposedly smart, right? So, and that's what people are buying then, smart toaster. Even in this COVID scenario, people are buying smart toaster, smart iron. I don't know what that is. But anyways, so the point is, it's the world of IoT. So everything is connected. But the problem is, all these devices are limited power. Because previously, you're talking about desktop is always connected to the power. But now, you have these small devices like smartphones or smartwatches. They don't have unlimited power. They're not always connected to the power source. So that is something. So the point is, these trends are happening, but then the question is how they're impacting energy and power. So that is I'm trying to discuss here. Second trend is from cyber to cyber physical. So previously we have cyber world different, physical world different. So you have manufacturing, a factory which is separate from computation, which is your computer and stuff. So you have factory and a factory which is making cars separated from your machine, a server, something else. But now everything is like mishmashed. Cyber physical. So a smart manufacturing. You have industrial IoTs, and this is sensor actuator network. So you have physical space being sensed, generating data, going to the cyberspace, getting processed using AI or artificial intelligence, getting some information, that information coming back to the physical world as actuator, and then giving feedback, and based on that, physical world is changing. So a continuous cycle of sense, collect, process, and feedback. And that requires high reliability, high capacity, and low latency. Trend 3, from batch processing to artificial intelligence. So you have regular processing of like one job after another, and now it's all artificial intelligence, like multiple parallel complicated processing at the same time. So you have face recognition, voice assistant, object detection from drones, all of them collected to different use cases. You have autonomous driving, you have smart healthcare. So you have machine learning, deep learning, AI jobs requires high capability in terms of processing. At the same time, they require more energy, not less, because previous batch processing required less energy in comparison to what we have now. So that's a problem. And then finally, you have the final trend of bringing cloud closer to you, bringing cloud closer to earth, or rather to the data generation side. So what is that called? That is called edge computing or fog computing model. So previously you have all data being sent to the cloud, getting processed, coming back to the devices. But now you have this processing which was connected to the cloud. The idea is, why don't we bring the processing closer to the data site? So you have a smart building or some devices, vehicles or human sensors or health sensors. They all have processing locally, because what you want is you want to bring down the latency of data going to the cloud and the process data coming back, because it adds a lot of time latency. You want to bring that down because we want things quickly. And these are mission critical applications like healthcare. You don't want information to get processed remotely, and also you don't want information processing taking time. So you want these processing locally. So that is edge computing, distributed computing. But the problem is, all these devices now, they have limited energy budget. Previously, cloud was like data center. You don't worry about energy. But with edge computing, you have to worry about energy, because you're talking about small devices which are not connected to power source. So you see what is happening. We are going towards a world which requires more energy, but the devices, the reality of the system is we don't have a lot of energy. So there is a trade-off. There is a increasing curve and there is a decreasing curve, and you have to balance these two things out, and that's where the technology is headed. So from 5G and beyond, you have the previous generations of technology which are driven by devices, but now you have 5G and mostly 6G driven by human beings and driven by applications. So rather than having one solution for everything, what you have are tailor-made solutions. So the reality from 5G to 6G, or the vision of that, again, it's a very busy picture similar to what we already saw from 4G to 5G. But here I want to, the takeaway from this picture will be, one of the driving forces of 6G is extremely low energy consumption. So everything you do, collection, processing, analysis, it has to be low energy. So for 5G, energy efficiency was a byproduct, not a driving force. But for 6G, which is the next decade, or maybe a couple of decades, who knows, one of the driving forces is energy efficiency. And that is the difference. And that is what I want you to take away. Like the driving force, one of the driving forces for 6G is. And so this shows how the technology in terms of wireless communication is changing. So on this axis, you have the frequency, like higher frequency communications, which are complicated in terms of hardware design. And here you have the coverage. So coverage is increasing. Previously, we were talking about cellular data, small cells like kilometers or miles in terms of radius. Now we're talking about larger networks like satellite communication or underwater communication, where the coverage is hundreds or hundreds of kilometers and miles. So that is something where those are areas where energy, because the devices cannot support more energy. So you have to come up with solutions which require less energy. So that's 6G and those things, where you are communicating at higher frequency and higher coverage. Power efficient transmission is important driving force for 6G development. So to conclude, big data and heterogeneous devices and better experiences driving the evolution to 5G. But then at 5G, we see some clear trends emerging with Internet of Things, cyber physical systems, artificial intelligence, and edge computing. And these trends are creating novel trade-off problems for energy efficiency, because the reality is what we need for tomorrow requires a lot of energy, but what we have for tomorrow has less energy. So how do you balance that? So power and energy efficiency is a key motivator for next decade of digital transformation and innovation. And so this workshop or this symposium is fantastic and very timely, and I hope it can bring some new ideas, new innovations, and people who are working in this space has like the space is super hot, and people who are working in this area are doing a lot of great work, which will drive the next generation of innovation. So with that, I thank everyone again for inviting me to this workshop, to this symposium, and I hope that this talk of some use. Thank you so much.
Thank you, Dr. Debaroy. Thank you so much for informing us about the processing of data being a challenge and how to move from cloud to an edge. With that, I think we'll move on to the last speaker of the session. That is Mr. Nitin K. Mohan. He's a product specialist in Hydac Private Limited, and his areas of research are electronic sensing technology, condition monitoring, hydraulic systems, and IoT and IIoT. He has done his BTech in instrumentation, and he has 7 years of experience. So over to you, Mr. Nitin Mohan. Hello, Mr. Nitin Mohan.
Mr. Nitin Mohan, I think you're on mute. Can you unmute yourself, please? Yeah, now I can hear you. You may please start. We're not able to hear you well. Can you just raise your mic volume? You can log back in, I think.
Hello.
Yes, Mr. Nitin, please go ahead.
Yeah, okay, fine. Thank you. Sorry for that. I hope my voice is audible as well as my slides are also visible to all.
Yes, yes.
You can just check if the slides are changing as well, right? Yeah.
Yeah,
okay,
they are.
Fine.
Please go ahead.
Yeah. Sorry. Yeah. So once again, thank you all for for giving us an opportunity, especially to IIP for introduce or giving us an opportunity to show this virtual conference on this particular day, Environmental Day occasions. So we will be more focusing on a topic which we call it as an agenda, this condition monitoring as enabler for Industry 4.0. So why we wanted to introduce this particular topic on this day of session is this is going to be a very useful tool and technique to give a smart energy efficient machines in some of the industry sectors which we are dealing with. So we represent hydraulic industries, So we do provide solutions in hydraulics. So all these presentations probably our contribution in energy efficient machines making will be condition monitoring as an enabler for Industry 4.0. So let's start with a classical or real life examples of finding a restaurant to have a dinner. Probably when we are stepping out with, or we are in a traveling along with our family and reach a particular city or location which is not familiar to you. So probably when you are wanted to have a dinner, you will have to find the solutions to find out a better restaurant to have a dinner along with family. You will be having many criteria like food quality should be good, and hospitality should be good, and also it should be a nice ambience for the family networking to be known. So and when it was before this digitalization era, we probably get in touch with n numbers of people who is nearby to that locations over a telephone, and also a couple of friends also we will call, and we will ask a lot many people's regarding an appointments or opinion about a nice restaurant which is near to your existing location. So you probably have to do many numbers of phone calls and need to take opinion from them. So probably what you are doing there is actually wasting your energy, and you will finally fed up with asking many opinions. And also, of course, you cannot some of your friends or your family members or relatives whom you are not regularly in touch with them. You have to little bit more. You have to as a starting of introduction of the conversation, you have to start with a nice introductory statements as well, right? So you will be fed up with and your energy at the end of the day, and that is the situation, right? So it's a very real life case which we all have gone through. And now, after introducing, this particular digitalization and energy saving approach can be easily recommended here. How it is that we can see in the next slide, you can see one of the nice restaurant which is obviously we can consider in this slide as an example of nice restaurant which is near to your existing location, and probably lot many peoples are doing a networking dinner with in this hotel, and many of them are using the smartphones, and you will be always get a notification of many good hotels, right? So when it has also been possible for in current situations when you are stepping ahead or stepping out from a restaurant having a dinner, obviously the Google will be asking you how was your experience at this particular hotel, right? So this is nothing but this is Google is actually doing a data collection or an opinion collection from you people, and that is being posted in a digital platform. So obviously this I wanted to tell you is that the data is actually a new oil and a new energy saving technique also we can introduce when the data is made available to us, right? So obviously when we come to this example, your mobile phone is having its own inbuilt GPS sensor which will function as an position tracking, and based on that tracking on Google Map or on the global positioning systems, you will be getting notification how was your experience at the hotels, right? So that is what we are talking about Industry 4.0 in the digitalization era. So we are now here in Industry 4.0, which as my colleague, previous colleague has nicely explained about the data analytics, big data. So this itself is considered as Industry 4.0. And moreover, in Industry 4.0, you will get different possibilities for having an interconnection between the machines, and machines will try to talk to human, and human can also even talk to machines to understand their problems and rectify the problems. So this is how the Industry 4.0 comes, where the data analytics mostly occur, and it is called as the cyber physical systems, right? Lot many machine learning concepts, artificial intelligence concept, machine digitalization is happening here in Industry 4.0. You can see that the way we came from Industry 1.0, it's 1.0 first industrial revolution, we can say, which was purely mechanizing, and now we are at Industry 4.0. And also Industry 5.0 is also a hot topic which is being talked in the globally. So now, when we talk about the energy efficiency achievement in a machine, or the approach of machine efficiency or maintenance approach, efficient maintenance approach of the machines, we probably talk about two mainly: reactive and preventive. And in reactive and preventive maintenance, obviously there is no particular energy saving or cost saving happening, right? You can see this percentage of calculation which we did from our particular point of hydraulic industry. And then we came to know that in this industry 4.0, we should talk about predictive maintenance, which will give you some maintenance information, some early on a component failures or system failures information, probably 1 week beyond, or when the time of failure occurs. If you get an early indication of that information, would save a lot many energies and cost saving method. So that is predictive approach. And we are also, we can say that predictive, maintenance is estimating residual life expectancy, and we are also, talking about proactive maintenance. So that is actually increasing residual life expectancy. So we are having a closed loop monitoring systems for the hydraulic systems or machines, and we are doing the predictive and proactive maintenance for increasing the energy efficiency of their machines and also the productivity of the machine. And finally, to understand it in your breakdown, this optimum value, this is what we indicate, from the data analytics or from the data which we gain from that particular systems. So it is not too early or not too late. We provide an optimum call due to some algorithm running, and the easily easily scheduling of your maintenance or production can be easily done for the particular machines, right? So this is what the goals of Industry 4.0 or digitalization says, and that is this is one of the technology organization, and how for GmbH has been studied and provided this information. This is what we call it as improved process is the main goal of when you are implementing this Industry 4.0 on your premises, right? So when we talk about the hydraulic power units, this is what our area of interest. You will have to talk about the Pascal's law, obviously. So it's pressure, it's equal force per unit area, and that force is basically normal force, right? And there are many parameters which needs to be monitored in the hydraulic systems to ensure the productivity and should ensure the energy efficiency of the systems. And we should also ensure that there is no wastage of energy happening in the hydraulic systems. So all these parameters need to be monitored thoroughly and continuously, and thereby, we are providing the energy efficient solutions in stationary hydraulic systems as well as mobile hydraulic systems. So this is the real applications which we can easily show in one slide. And this is a typical classical hydraulic power unit which we usually serve to all type of industries like power, steel, or mobile hydraulics, or any kinds of industries which you find we are there is a presence of hydraulics wherever human power is, or the electrical power is not sufficient to drive them. So here also you can see there is a couple of motors here which is usually running on a electric energy. So this is kind of
Mr.
electrical
Nitin, I think your slides
energy.
are not being changed. Can you just change your slides?
Slide is not visible. Is it changing now?
No, no.
Is it?
No, it's the same slide.
Hello.
Yes, Mr. Nitin.
Yeah, is it changing now?
No, no, the slides are not changing. It's the same slide.
Oh, really? What has to be done at the moment?
Yes, and you'll have to really hurry up because we're running behind schedule.
Yeah, right.
Sir, you can just stop sharing for a moment and again, share your slide, and you can quickly, go to your slide of current presentation.
Okay, I'm trying to. Is it visible now?
No,
No,
not yet. It's not changing. It's the same slide.
Oh, really? Probably could be some.
yeah, you can stop sharing for a moment, and again you share.
Okay, I stopped sharing,
Yeah,
and now I will start sharing. Screen share desktop.
page is not changing actually.
Oh, okay. Not changing, right?
Yeah, not changing.
It's the same first slide.
Can I guide you through this, please? If you don't mind, can you please exit the slideshow first?
Sorry.
Can you please exit the slideshow first? And
Yeah,
exit
yeah.
the
I
sharing.
will.
Exit
I
the
will.
sharing as well. Exit the
Okay.
sharing.
Yeah, I exited the sharing and exited the presentation.
No, your slide, you haven't exited the sharing, it's still showing, so you need to do that. Please exit the sharing on Teams also. It is still showing on
Yes.
us. It is still showing on the screen, so it looks like you haven't exited sharing.
It's still showing.
Yeah.
No, I exited from the sharing.
All right. Let us do one thing. If you exit from the sharing, then now are the slides in normal mode or in slideshow mode?
It is in normal mode. Yeah.
All right. So reshare, but reshare in normal mode. Reshare again.
Yeah.
As far as I can see, it's still on the screen, so I don't think the sharing has exited from your side.
Is it now?
No. Just a minute. What I'm going to do, I'm going to disconnect you. In case you actually get knocked out of the call, please dial back in.
Okay.
Just a moment. I'm just trying to see whether I can try to disconnect you from the slideshow. Okay, just stay on the line, please.
Yeah.
All right. Now please exit the slideshow again.
I exited the slideshow and also
Exited sharing.
I pressed the share.
No, yeah, you need to press the share. There'll be an X over there. Press the X, please. After you press share, you should see an X.
Yes, I pressed the share button, but it's showing screen share and desktop or window.
Yeah. So do window and scroll down to the window that you want. Scroll down to the slide to the files. Underneath, you should see all the windows. Just select the. Yeah. Excellent. Is he there? We lost him again. A little bit of an issue here. It's taking up time. We'll need to wait for him to dial back in. he's not on. Could one of the organizers please phone him and see whether he's able to dial back in, because he's not on now.
Yes, sir, we are trying.
Happened? He's not in the system. He was trying to dial in and he got, it showed him as joining and then leaving.
I think there is some problem from Nitin sir's end. So I request Poonam Gupta ma'am, the session chair, to conclude the session, and we can move on to the next session.
Okay, fine. So there seems to be some technical error. So we come to the conclusion of this session. I would like to thank all the speakers and the participants. And I would like to now hand over to Dr. Vipul Sarkar, who will be chairing the next session. Thank you.
Thank you, ma'am. Next, move to the last session, which covers the advanced material for energy application. And our first speaker is Dr. Venkataraman.
Can you all hear me?
Yes, please. Very clearly.
Professor of Department of Chemistry, University of Massachusetts, Dr. Raman has several awards in his credit, which includes NSF Career Award 2020, CSIR-IIP Technology Award 2005 and 14, Dow Distinguished Lecturer, University of California, Santa Barbara 2011, University Distinguished Teacher Award at 2015. And many more. With that, I am handing over to Dr. Venkataraman to talk on hybrid sites.
Thank you. First, I want to thank the organizers, Dr. Sadal Kumar, Dr. Anjan Ray, and the organizing committee and Team Sefco 2020 for putting this together. I know it's hard to get everything going in the technology side, but it's great, and it's good to talk about science when we're all shut down here, particularly US due to COVID. I'm going to talk to you about this new area of research, which started about 6 years ago, which are called the hybrid perovskite solar cells, and what's the promise of these solar cells, and what are the challenges actually in this field. And so, and I'm pretty sure many of you may know this field already, so I'm going to give you some brief overview for people who don't know this, so bear with me as we start talking about some of the basic chemistry of these systems. So we all know about silicon solar cells, which is very common in many places. And this is actually considered to be what is used for generating large amount of power as a replacement for some of the current technologies. And it's a very reliable technology in terms it's been around for a long time. These are typically very stable, and they have an efficiency which is about 15-20% in the large scale production. And so these are all positives for this technology, and that's why it's been widely adopted in all places. But some of the negatives actually are that these are extremely thick, they're opaque, and they're very heavy. And getting silicon out of silicon dioxide is not easy. It's very expensive to manufacture and install, and so that's one of the major problems. And from a scientific perspective, the efficiency has plateaued, and I'll show you the graph of how it's plateaued. And so basically, the technology is mature in many ways, but it has some of the issues that is inherent to the technology. So this led people to look at another class of solar cells called the thin film solar cells. And one of the major advantages of these systems actually are that they are typically very thin, light and semi-transparent. They are very easy to manufacture and install. And one can use these for a wide range of applications. You actually heard a talk about IoT and about the power needs for like a smart toaster or a smart iron. And you need to get a power for this, and you actually don't have to plug into the power source, but might actually have a thin film solar cell attached to the side of it to power these systems. So one of the main concerns with this technology has been power efficiency. And more recently, another concern that cropped up actually is that they're not very stable long term. So when you put a silicon solar cell, typically you can actually have this running for about 10 to 20 years without any major issues. Whereas these things, they're not very stable for such a long time. But also, the fact that they're very thin and light and semi-transparent allows us to think about applications that are not just based on silicon. So one can imagine putting this on windows, one can imagine putting it on your coffee tables, or like in the back of your laptops to power using the light that you actually have in the ambient setting. So that's actually what is driving this field of thin film solar cells. And so that led to a wide range of technologies that are being explored. This is a very crowded graph, and so please bear with me for a second. And so, and you can see that what you see here is this crystalline silicon cells, and that's all shown in blue. And you can see that they're plateaued out, in terms of about 25-26%. What I want to bring attention to is this red box here, and you would see here that there is this technology that's called the perovskite that came about. And that started off, pretty low. In fact, it started with 3%. And in about 5 or 6 years, it's already climbed to about 25.2%. And in fact, it has now overtaken multicrystalline silicon in terms of efficiency. And so this is what is exciting about this technology, is that in a short span, the efficiency has gone from about 3% to all the way up to 25%. And so, and that's what is driving this field, is that it is competing now with silicon now. It has overtaken multicrystalline silicon. And so why is it this technology still not out there in the market for applications? So to understand that, we're going to look at this compound called perovskite. It's a very old mineral, but then it's been reformulated in a very different way. And so the perovskites that we're going to talk about today have a nominal formula ABX3. Where A is the methyl ammonium. This is the A cation that's sitting in the center of the space here. And then you have the lead, which is actually the center of this octahedra. And then you have the halide ions that actually are here. And so this is a very ideal structure, and so typically it's called a cubic perovskite. And of course, there are other versions of it that we don't have to worry about for this talk. But in general, you actually think about like a big box with the methyl ammonium sitting in the middle. Now, this is going to be important as we understand why some of the problems with this particular system. And so, as I said, the technology really began only a few years ago. And so, first time this paper in 2009 came out, the efficiency was about 3%, and people did not pay attention to it at all until in about 2012, when Miyasaka and Snaith actually published a paper in Science, which had a 10% efficient solar cell, and that really caught the attention of people. And the reason I'll explain a little bit later why it is so important, because when 2012 paper came out, it just took the PV world by surprise. So as I told you before, one of the major advantage of this technology is that it is very highly efficient. It actually has a very high theoretical potential also. You can actually go to about 30% in a single junction solar cell. And in fact, people are predicting that if you combine that with silicon, you can even go to more than 40%. And as I told you, you can apply for a wide range of applications, from like standard, production of power to like, IoT type devices where you can actually add it to any device that you have. It has a very tunable property. The chemistry of it actually is very good in terms of changing the halide ions, changing the counterion that's in the middle of the box. And so that actually is very useful. And it starts off with inexpensive, abundant precursors. One of the major reasons why this technology got so exciting was that it is based on low temperature solution-based fabrication. If you've never done this technology, if you're not even a chemist, for example, and then you go to the lab, you could actually make a cell today which is about 5 to 10% efficient. That's how easy it is, this technology-wise. And so the previous technology people are looking at are the organic photovoltaics, and that required a lot of synthesis, that required a lot of technical skills. This one, the fabrication actually was very easy, and you can make it with thin, flexible, and semi-transparent films. One of the major issues with it is that it is pretty unstable to a lot of things. And it's unstable to heat, humidity, applied electrical bias. More importantly, it's unstable to light. Now, that's interesting because you're using this as a solar cell and the compound is not stable to light. And that's the challenge that we're going to talk about today. And that's, it took us a while to understand this because the field grew really fast and some of the fundamental properties actually were poorly understood. And it's a very complex system. It looks like simple chemistry, but we are now learning that it's quite a complex system in terms of how the system behaves under light. So what we first found was that, as I told you, it's very unstable light, and this degradation efficiency, this is what you're seeing here, is the power conversion efficiency. And if you've not heard this term, it's a very simple term that you make a solar cell, which I'll show you later on. You simply calculate how much power you put in, and you calculate how much power you get out. And then what you're doing is you normalize the maximum power, and then you actually watch the solar cell under illumination what happens, and you can see here that the power conversion efficiency drops down pretty quickly, and that is actually the problem in this system, one of the major problems. The other problems of humidity and water affecting this can be solved by good encapsulation, but light, that's a major problem. So this is where we began working on this, and this is my team here at UMass. The work actually began, with Dr. Monojit Bagh and Larry Rena. Dr. Monojit Bagh is now a faculty in the Department of Physics in IIT Roorkee, right in your neighborhood. And so it's been continued by Christy Cutting, Hamza Javed, and Emily Smith, and recently Zhao Jizang has joined the team, and it's been funded by the U.S. Army through the U.S. NATIC Center here in Massachusetts. So what Monojit and Larry started looking at was like, why is it degrading really fast? Why is it degrading under light? And what is actually going on? And so as a chemist, the first thing that you think about when this actually happens is that, is it photochemical? Is it actually something that's actually degrading irreversibly so that you cannot get it back? So to test that, we started making a solar cell, and we used this particular configuration which worked well with us. And this actually is in the field is called the PIN configuration. And it's also what's called a planar configuration. So we chose this particular architecture because it's easy to fabricate, and when successful, we can easily translate that into large-scale production. So the way we do it is that we place ITO, and then we coat P.PSS, which is actually a polymer that is in the whole transporting layer. And then we make the perovskite on top of it. And the perovskite actually is made very easily. You can actually make methyl ammonium iodide, or you can just buy it now, and then you mix that with lead iodide to form this MAPBI3. Now, for those of you who might remember high school chemistry, if you have done like a lead confirmative test, you actually would remember the golden spangle test, where you take lead iodide, you get potassium iodide, and then you actually heat it, and then you cool it back, you get these golden spangles. This reaction is exactly the same as that, except that you replace the potassium iodide with lead iodide, and you make this very highly colored compound, which is called the methyl ammonium lead iodide, which is what goes into the perovskite. And then on top of it, we put a electron transporting layer, which is PCBM, and then you coat the electrode, which is calcium aluminum. We've now changed to silver at this point. So you make this device, and when we first made the device, we got about 13% efficient. And then we obviously wanted to study how stable this device is under light. So what Manojit did, which was very interesting, was that he initially studied under light, and you saw the curve where the degradation was happening. But then, as we were actually looking at why it actually was degrading, we actually had assumed that the central, one of the ions may be actually moving. And there are clues in literature that indicated to us that the ion actually may be moving under light. And so what Manojit was doing was to shine the light on, measure the efficiency, and then shut off the light, and then see what happens in the impedance. And what he found was, when he came back and did the measurement again, that you can see here that he shuts off, and then he waits to do the impedance, and he comes back, and you actually see the efficiency goes up. And this pattern actually is happening, which is that you have the light on, the efficiency goes down, switch off the light, wait for some time, and it looks like the system anneals, and then the efficiency comes back in. So what this told us actually was that the degradation was not photochemical, it's not completely irreversible, it is quasi-reversible. And that actually is what made this whole thing interesting. And so I'm skipping a lot of details here, but I'm happy to talk to you if anybody either now or later on. And so we used electrochemical impedance spectroscopy to study the ion diffusion. And what we found actually was that it looks like when you change the ion, the central ion, from methyl ammonium to formamidinium, you can actually see that the diffusion coefficient drops down, which is indicating that probably that the central ion that's here is what is responding. Light is actually probably moving, and that's what is causing some of the degradation. So our hypothesis actually is that light comes in, and we don't understand why it moves under light. We have some ideas, but then once it moves, it actually probably gets stuck at some defect site or a grain boundary. It cannot come back, and then it degrades to lead iodide and the methyl ammonium iodide. So we also found that the barrier for this activation energy, for the ion to move, matches well with some of the computations. And so that gave us the hypothesis that under light, maybe the halide is moving, which we cannot see because it's very fast, but certainly the methyl ammonium actually is moving under illumination. And so our hypothesis actually is that, well, if you slow down the ion transport, it'll increase the device stability. And that's actually what we started to work on. And so how do you stop the ion from moving, right? So now you quickly see that there's a barrier here, which is about 0.5 eV to move. And so if you don't provide that system the energy to move, then probably it'll actually not move. So to test this hypothesis, we did a couple of things. We, first of all, made the device and then placed it actually, under some cooling. And this is the blue curve here, you see it, and you see that it's stabilizing somewhat. And then, we also found out that if you cut off the infrared from the solar radiation, which heats up the cell, or if you actually use a white LED that does not have the infrared component, then it's actually pretty stable. And so this is indicating to us that if you do actually, somehow slow down the ion transport, the stability actually can be increased. So, but that's obviously not the solution, right? We don't want to actually have an air cooler for the photovoltaic, or not completely use the solar spectrum. And so what we wanted to do actually was, if this is physical methods that are actually happening there, can we actually do the slowing down using chemical methods? And so we started actually playing with replacing that central ion that you saw, methyl ammonium, with formamidinium ions here. And what you see here is that indeed, that as you start replacing with formamidinium, the stability actually is slightly better. And so we don't, in this case, have to use cooling devices, but then it's very clear that the infrared actually is now having some effect of it. So you can see the LED actually is flat, but if you put the solar simulator, it's not. So this is indicating to us that it needs to be further stopped. So at that point, we started looking at much larger ions. And so, imagine again a box here, and then your central ion is there. Whatever ions we choose here, we're replacing that ions to go into this box, right? Now, you also quickly realize the problem that may come from the chemistry perspective, which is that the box actually, the size of this box actually is somewhat fixed. So you can't put any ion in the middle because it has to fit the box, right? And so this has been at a point where we were stuck for a while because you can't simply take, and then try to get some of these ions from the box. So now we figured out that if you do make this perovskite with this methylammonium ions, and then it turns out that you can actually exchange some of the methylammonium ions with these other ions, right? And so, when with these larger ions go, the box expands somewhat little bit, but if you put too much of the big ions, then the box certainly will expand and actually will break. So you can't put a lot of these ions, but then you could put some amount of these large ions to replace the methylammonium. And so that's a trick that we had played. And what we were able to do is to make these devices with these various ions. And you can see now that if you remember the first slide I showed you, that we actually had about 13% efficiency. We're able to actually now go up to about 18 to 19% with formamidinium ions. What you also see here is that once you introduce these large ions, it has flattened out. The degradation has flattened out. It's become more stable. And that indicates to us that we are moving the right direction, that when you replace the methylammonium with large ions, and you don't need that much, even 5% actually is enough to block any of the ion transport, it seems. And so when you look at the stability, it has increased a lot, and that's a good news, right? What you also see is that the efficiency is not the same. So what we wanted to see actually was, well, how would you change the efficiency? And so we can actually, our champion cell was this formamidinium cell that we had used with about 18 to 19% efficiency. And so we wanted to see whether we can play with that. And so one change we made was that, and I'll show you the structure of this compound, PVBTSO3, we had, what happened? Somebody is sharing their slides. Let's see. Okay, can you all see my slides?
Yes, sir. Yes, sir. We can see your slide.
Yeah. So, right. So at this point, the PVBTSO3 actually was the one that we had worked on. I'll show you the structure in a second. And so when we're looking at P.PSS, if you remember, in the slide, I actually used the P.PSS here as a whole transporting layer. And it turns out that has a lot of impact on how you actually make this MAPVA3. And so, and it actually controls how the nucleation actually happens. It also controls how the perovskite actually grows on this. So we made like two changes to the device. One actually was to change the whole transporting layer, which is not our invention anyway. People have been playing with this whole transport layers a lot. But we also introduced a second layer on the top, which is C60N. Again, I'll show you the structure in a bit. That allowed us to move away from calcium, aluminum to silver. So in this case here, people have looked at the whole transport layers, and so they have looked at the PVBTSO3 is actually this one here, which we have been using, and this is P.PSS. But people have looked at other organic compounds too, and so if you're in the area of conjugated polymers, this is actually a rich area to explore on how to design this new whole transport layers that allows us to grow the MAPVA3 the way you want it. And similarly, other systems like amines and all this stuff. And so when we started replacing that system with PTAA, which is polytriaramine, which is a commercial one, and with copper iodide, which is an inorganic one, we can push the efficiency to about 20%. And that actually was exciting to us. But it turns out the stability of it, I think, was not great. So then we made like one change that actually was important, which was that we discovered that if you look at the energetics of... Yeah?
Can you conclude within 2 or 3 minutes? Please?
Yep, I'm almost done. Last two slides.
Thank you. Thank you.
Yeah. So if you look at the energy levels of the P.PSS, it sort of worked well because it actually is rightly batching with perovskite and other stuff. But as copper and PTAA are quite far away, and so we actually made one change, which was that put the PTAA and copper iodide together. And so when we did that, what we can see here is that we've been able to push it to about 21% efficiency with the system. And then when you study the stability of the system here, you could actually see that it's actually pretty stable over a long time. And in this case here, you see the efficiency we are monitoring now. We're still actually monitoring this device now, and it looks like it actually is pretty flat. And so this is where we are, where you're able to actually change the counter ion, you're able to change interfaces, and you're actually able to get very high efficiency. And so where we are now is to probe the light cycling, meaning that we're looking at these devices in the real world and see how stable they are. And then I'm pretty sure it's not going to be stable at 10,000 hours. So we may have to tweak the whole transport layers, and then do the stability studies actually under light, humidity, and temperature conditions. And the next step actually is to make the large area devices, which is what we're actually heading to. And so with that, I'll actually end if you change the counter ion, if you change interfaces, you can actually get these efficient devices. And again, the long-term stability is the one that actually is important for us to work on. And that's a rich area to work on because you can actually think about devising new whole electron transporting layers, which actually can increase stability. With that, I'll stop and I thank you.
Yeah, thank you. Thank you, Dr. Venkatraman, for enlightening us with the proboscide material for energy harvesting. Our next speaker is Dr. Venkatakrishnan. He is Associate Professor in IIT Mandi. Prior to his engagement as a professor of IIT Mandi, Dr. Krishnan done his postdoc from University of Pennsylvania 2006 to 2010, National Institute of Material Science, NIMS, Japan, 2010 to 2012. After joining IIT Mandi, he sharpened his research in the field of heterogeneous catalysts for energy and environmental application. With that, I am handing over the virtual platform to Dr. Krishnan. Dr. Krishnan, please.
Yeah, thank you very much for your kind introduction. Let me share my slides. So, is it visible now?
Yes, it is.
Okay. So, let me make it also full screen. Yeah, it's better now. Can I?
Yeah, it is.
Hello.
Yeah.
Okay. Fine. Yeah. Thank you all once again for your kind introduction and also for your kind invitation to deliver a presentation in this conference. So today I'll be talking about design development of nanostructured heterogeneous catalysts for energy and environmental applications. And this is my research group, and I would like to acknowledge all members of my research group. This is my present research group, and also I acknowledge the former research group members as well. It's they who have done the work, and I am presenting in front of you. So our research focus is on development of the nanostructured heterogeneous catalysts, and in this case we are working in the field of photocatalytic water splitting, photocatalytic pollutants removal, and biomass conversion to valuable products, and also on other areas such as the bioinspired scaffolds for dip catalysis, catalysts for green organic synthesis, and in situ studies of the catalysts in action. And for today's presentation, I'll be presenting only on two of the aspects, mainly the photocatalytic water splitting and the biomass conversion to the value-added products. So in photocatalysis, our main objective is to utilize the solar spectrum, the total solar spectrum. So how best we can utilize this total solar spectrum? The solar spectrum is given here, which consists of 5% UV, 43% visible light, and 52% near infrared radiation. So when we discuss about the photocatalytic water splitting, I hope most of the audience know about the water splitting. It's mainly for the hydrogen evolution, wherein hydrogen could be used as a fuel. It's a renewable fuel. So we want to develop a new catalyst which can be very effective for utilizing the maximum region of the solar spectrum, and the material should also be low cost in nature. So in this regard, we chose zinc oxide, which is having a band gap of 3.37 electron volts. It's a low cost material, but this material is not active under visible light, but it could be made active by different strategies. So one of the strategies that we had used in this case was we took the nano-sized zinc oxide and doped it with varying amounts of MOS2, the molybdenum disulfide, and reduced graphene oxide to make a ternary heterojunction nanocomposite. And in this case, why we used reduced graphene oxide? Because this is analogous to graphene and it has a 2D network type of structure with the sp2 hybridized carbon atoms, and it has several good properties. And MOS2, the reason for us to use this MOS2 material is it has a stacked layer type of a structure with the sulfur atom on the exposed edges, which provides kind of like a sticky edges to the hydrogen ions in the solution, which will aid the hydrogen production. And just to tell you about how we did the material synthesis and the characterization, we used a hydrothermal reaction technique to prepare the material. So we prepared the graphene oxide nanosheets, and then we reduced it hydrothermally to prepare the reduced graphene oxide. And during this process, we also incorporated the MOS2 and MOS2 in the RGO nanosheets. So you can imagine the RGO as a big carpet type of a thing, and the MOS2 are again another 2D materials, something like a foot mat type of a thing which is sticking on to it. Then subsequently, again using another hydrothermal procedure, we dope the zinc oxide onto it. Whereas the zinc oxide is the nanospheres, and zinc oxide is the predominant material in our nanocomposite. And then subsequent to the preparation, we did a detailed characterization of this material using several techniques, which includes X-ray diffraction, which clearly indicated the presence of zinc oxide in all the nanocomposite material. And due to the very low percentage of the molybdenum disulfide and the RGO, we could not see it directly in the XRD pattern except for some few peaks. And we also did a detailed characterization of the morphology of the material using transmission electron microscopic technique, which is shown here. And we could observe the heterojunction formation using the TEM technique. And apart from that, we also did the EDAX data to confirm the whatever elements which are present in the sample. Then subsequently, we did a very detailed analysis of the electronic structure of this material using the XPS technique. And due to the limitations of time, I'm not going into the detail, but we have performed this analysis, and we were able to study what is the oxidation state and what is the electronic structure of the elements present in our nanocomposite. And subsequently, we did further characterizations, as I was telling you about the Raman. So in the Raman characterization, we were able to see clearly the D and the G bands, which correspond to the reduced graphene oxide material, apart from the other bands which correspond to the other elements which are involved in this material. And then we also did the DRS spectrum. DRS stands for the diffuse reflectance spectroscopy, wherein we studied absorbance as a function of the wavelength, and we can see that the absorbance increases in the higher wavelength region, which indicates that the material becomes active in the visible light region, because ZNO is a UV active material, but the combination of this material, the final prepared nanocomposite, is active in the visible light region as well. And we also did the TGA, which indicated the thermal stability of the material. Subsequent to all these detailed characterizations, we did the hydrogen evolution experiments, the photocatalytic hydrogen evolution using the direct sunlight. And as you can see, we prepared nanocomposites of varying compositions, having molybdenum disulfide and RGO in several compositions like 2, 3, 4, 5, 6, and 10 MOS2 RGO present in the overall sample. So when we see this graph, which indicates the volume of the hydrogen evolved, we found that there's a lot of hydrogen which is being evolved. The amount is about 28.16 millimole per hour per gram. So for one of the samples, which is the ZMG4, which contains 4 weight percentage of MOS2 RGO in the overall nanocomposite. And the main reason for this composite giving the best hydrogen evolution is, this is an optimal amount, and before this one, these are not the optimal amounts. So, but beyond this, again, this dark colored material, the MOS2 RGO, this covers the zinc oxide material, which is the main semiconductor, and there is a blockage of the light which can reach the main semiconducting material. So that's the reason this 4/8% sample is exhibiting the best catalytic activity. We also studied the variation in the amount of the photocatalyst and studied how the volume of the hydrogen is evolving, and we found that 10 milligrams is an optimal amount. Even in the lower amount like 5 and 3 milligrams, we are also able to get some appreciable hydrogen evolution. We also did a detailed recyclability analysis. So after performing the photocatalytic experiments, we were able to recover the catalyst and then do the recyclability for 5 cycles, and we were able to get good reproducibility. Now, coming to the question why this particular material is interesting and what is the mechanism behind the hydrogen evolution. So in order to understand this, we kind of took the recovered material, the recovered catalyst, and did detailed characterization of this recovered catalyst. And interestingly, we found that there is a zinc sulfide material which is evolving during the process of the reaction, and the source of the sulfur is this sodium sulfate with sodium sulfite, which is being used as a scavenger in our reaction. So that becomes the source of the sulfur, and this in situ formed zinc sulfide is making the number of interfaces much larger. So there is an increase in the transfer interfaces, and this leads to the better hydrogen evolution activity. And overall, we could observe the synergistic effect of these two 2D materials. One is the MOS2 and the RGO, and this provides abundant exposed reaction sites, which are good for the hydrogen evolution. And this work was published in the year 2017 in the journal ChemSys. And as a follow-up of this work, we also did another work wherein we doped the zinc oxide with nitrogen and supported it on the graphitic carbonitride nanosheets instead of the graphene. So this is a binary nanocomposite material, and this work was also used for the photocatalytic hydrogen evolution, and this work was published in the International Journal of Hydrogen Energy. And then we also did other modifications in our material, wherein we prepared another binary nanocomposite material with defect-rich MOS2, and again observed a much better photocatalytic hydrogen evolution activity. And this work was published in last year in ACS Applied Energy Materials. And we also wrote a review article in Catalysis Review, which will be published sometime soon. This is again based on the zinc oxide materials for photocatalytic hydrogen energy and also environmental remediation. And due to limitations of time, I will not be talking in detail about the environmental remediation. And another work which I would like to present today is on biomass conversion. So biomass, we all know about the availability of biomass, and biomass could be a very good resource for the future energy applications. And one of the main reactions in the biomass conversion is the converting saccharides to another useful products. And one of the very useful product is this 5-hydroxymethyl furfural, which is called as 5-HMF. And this reaction is already quite well known, but most of the times this reaction requires high temperature, pressure conditions, and also certain catalysts which have noble metals and quite expensive catalysts, and also the solvents which are used in this reaction are non-green in nature, which means environmental not friendly in nature. But what we have done is we have prepared a catalyst which can do this conversion reaction in green solvents. And the strategy what we have used in the preparation of this catalyst is we took a sulfonated graphitic carbonitride. So this graphitic carbonitride has Bronsted base sites, and the sulfonation of this graphitic carbonitride provides the acid sites to this. So it is a catalyst which contains both the Bronsted base and Bronsted acid sites. And we used different saccharides like glucose, fructose, cellobiose, sucrose, and starch, which is the monosaccharides, disaccharides, and polysaccharides. And we were able to selectively convert the saccharides to the 5-HMF. And we have studied the reaction under different green solvents, which includes water, ethanol, isopropyl alcohol, and dimethyl carbonate. And the formed 5-HMF was converted to various different value-added products, which are shown here. In the interest of time, I'll just briefly mentioning about this work. As usual, we prepared the catalyst using the hydrothermal strategy, and then we did a detailed characterization of the catalyst, the XRD and the Raman spectra of the catalyst material, the graphitic carbon nitride and the sulfonated graphitic carbon nitride are shown in these plots. Then we also studied the FTIR and the TGA plot of this catalyst. So the FTIR indicated the sulfonation and the functional groups corresponding to that, and the TGA indicated the thermal stability of this catalyst over quite a good temperature range. Then we did a detailed morphological characterization of the catalyst. The SEM and the TEM images of this catalyst are shown here, which indicates that the formed catalyst material has a sheet type of a structure. And we also did the EDAX and detailed elemental mapping of the catalyst, which showed the presence of all the constituent elements, including sulfur, oxygen, carbon, and nitrogen. Subsequently, we did a detailed XPS analysis of our sample. The XPS survey spectrum of GCN and sulfurated GCN are shown here, along with the individual XPS spectra of the different elements. And the atomic percentages and the binding energies are also indicated here. So we did a very detailed fitting and detailed study of this material. Then this is the reaction which we...
Can you please conclude within 3 or 4 minutes?
Thank you. Yeah. So this is the reaction which we studied, and we did a detailed optimization for the catalyst, and temperature was 200 degrees centigrade, which provided the best temperature. And we also optimized the time and also studied the different catalyst variations from different variations of the substrates from glucose to starch. And with the different solvents also, we did a detailed study of the optimization for both the monosaccharides and also the polysaccharides. Then our catalyst was also recyclable, and we studied the recyclability of the catalyst, and the catalyst was found to be stable even after 5 cycles of the catalytic activity. Then we studied in detail the green metrics associated with our catalyst and the conversion of saccharides to 5-HMF, which is shown here in this plot. And as I mentioned earlier, the formed product, the 5-HMF, was converted to other useful products as shown here. And finally, this work was published last year in the journal Green Chemistry. And summarizing, our group works in the field of nanostructured heterogeneous catalyst, and the applications are quite various. And finally, I would like to acknowledge once again all members of my research group, the faculty colleagues, research collaborator, and our instrumentation facility center, the Advanced Material Center. And these are the funding sources which helped our work. And thank you all very much. Thank you.
Thank you, Dr. Krishnan, for the brief presentation on development of nanostructured heterogeneous catalyst for water splitting and all. If there are any questions, so please. So there is no question. So we move forward to our next speaker. It's Dr. Ashish Bahuguna from Hebrew University, Jerusalem. We'll be talking about palladium CNX catalyst for hydrogenation reaction. So may I request Dr. Ashish, please be on time. So please take 10 or 12 minutes for finish the presentation.
Hello, am I audible?
Yeah, you are. Yeah, you are.
The slides visible?
Yeah, the slide is visible.
Okay. Okay, just let me make it full screen. Is it fine now?
No, it won't come if you do it that way. You have to go select the full screen version and then show that.
Okay.
Yeah, it is better you just show it from here. This is okay.
It's fine now?
Yeah, can you just change the slides and let us check? Can you just change the slides back and forth? Can you just go back one slide just so that we know that it's working? No, I think you are showing us the PowerPoint, whereas you are seeing the PowerPoint show. So that won't work. Please,
okay.
What you need to do is you need to exit this. You need to exit the share on Microsoft. Okay. And then go back and share the PowerPoint show.
Okay.
Not the PowerPoint presentation, the show.
Okay, let me try once.
Yeah. Right. Okay, now you're back on PowerPoint. You're back on the presentation, not on the PowerPoint show. You're not on the slideshow, you're on the presentation.
Okay.
So if don't do the slideshow, just present from here itself. Can you move the slide? Can you just move the slide by one?
Okay, let me just try. Is it fine?
Yes, working nicely. Thank you.
Okay, thank you very much. So, good afternoon, everyone. I wish happy World Environment Day to all of you and all the participants and audience. First of all, I would like to thank the organizers for giving me this opportunity to present my research work here. So before going into the detailed formality, I'll start my presentation of my research work due to time constraints. So as you can see from the slides, my presentation will be on palladium decorated functionalized carbon nitride, which is used as an efficient hydrogenous catalyst for hydrogenous reaction. And the interesting thing in this presentation will be potassium formate was used as a hydrogen source. So first of all, before going into the detail of the palladium decorated functionalized carbon nitride, first of all, I would like to discuss briefly about the carbon nitride. This graphitic carbon nitride is a polymeric structure having the alternative carbon and nitrogen in a hexagonal carboning, similar to the graphene, where the one carbon is replaced by nitrogen. Here we can see that it has various Bronsted basic functions, Lewis basic functions, as well as hydrogen bond motifs. So these are here. We can see that various synthesis method of these polymeric carbon nitride structure. So due to these various functions, basic functions, this material is very interesting material for the catalytic applications. And I'll be discussing one of the application of this material, although it is used for various catalytic application, including the hydrogen generation and various other applications for photocatalytic purposes. Now we see I will be talking about the functionalization of this carbon nitride material for catalytic applications. So these are the various functionalization that can be done on these materials. We can functionalize it covalently, non-covalently, by doping, by coordination interaction, and various other methods. So I will be discussing about the oxidative functionalization of this graphitic carbon nitride material. So what we did, we used the oxidizing mixture of this sulfuric acid, nitric acid in combination with hydrogen peroxide to functionalize this material. As you can see from the color, the graphitic carbon nitride is yellow in color, and after functionalization with this oxidizing mixture, it was converted into OGCN, which is a white material. And then for subsequent applications, we made a composite of this OxyGCN with palladium to make it a palladium functionalized oxidized graphitic carbon nitride. So what we did, the application of this oxidized graphitic carbon nitride decorated with palladium. So now here we can see that there are some interesting things what we observed while synthesizing this material. The GCN PXRD pattern, you can see that there are two peaks appearing for the GCN. This peak at 27.4 theta degrees shows it shows interplanar distance between the various layer of graphitic carbon nitride, while the peak at this 12.9 shows the intraplanar distance. Like here you can see the intrazine base structure, this distance, and in case of heptazine base polymeric structure, this distance. So the peak at 12.9 shows the intraplanar distance between the various layers. So when we oxidize this to OGCN, we can see that there is a distinct change at this 12.9 peak which is very different from the GCN peak. So when we correlated this peak with the PXRD pattern of graphene oxide, we saw that the similar functionalization as we see in graphene oxide, the peak at nearby this 11 theta degree, which is quite similar to the peak in oxidized graphitic carbon nitride. So we concluded that the material is highly oxidized when we oxidize with the oxidizing mixture, and it becomes similar to the graphene oxide, although it is white in color. So the material became very interesting for the catalytic study. So from here, in addition to this, we also did the solid state C13 NMR of this material, and we can see in GCN, the graphitic carbon nitride shows only 2 NMR peaks, while in case of the oxidized material, we can see that the 2 distinct peaks were further. We can see that the functionalized graphitic carbon nitride is having several other peaks in the carbon 13 NMR, which shows that extensive functionalization of the material occurred. From the SEM images of the GCN, oxy-GCN and palladium GCN, you can see that the GCN material and OGCN materials, some images are quite different, which shows that extensive functionalization happened on the material. And moving on to the main part, which is the application of this. I am not going into detail of the other characterization details of the material, although we have done the various other studies like TEM, SEM, and XPS, and thermal studies also. I will stick to the application part, which is more important. So we used this palladium OGCN material for the hydrogen release application. So before going to the hydrogen release, I'll be briefly discussing about this formate bicarbonate cycle as a vehicle for energy and hydrogen storage and release. So here we can see that we used for potassium formate as a H2 release material. So we can see that when formate in the presence of a catalyst, it releases hydrogen gas and get converted into bicarbonate. This bicarbonate can be again catalytically charged back to the formate, hence making this cycle a sustainable cycle where the same catalyst can do the hydrogen release as well as the hydrogen storage. The only difference is the hydrogen storage can be done on at optimized pressure from 5 bar to 10 bar, while the formate releasing hydrogen cycle can be done at the room temperature to the 50 degrees centigrade. Although formic acid is also a good source of hydrogen, but when we decompose formic acid in the presence of catalyst, it leads to generation of carbon dioxide, and the regeneration, or we can say that the hydrogenation of carbon dioxide is a difficult and thermodynamically unfavorable reaction. But for the hydrogenation of potassium bicarbonate in the presence of a catalyst is an easier task in comparison to the reduction of CO2. So we took this formate bicarbonate cycle as a tool for the various hydrogenation reactions. So I'll come first application is the reduction of nitro group by using this PDOGCN catalyst, and we also did the comparative study of this PDOGCN catalyst with simple palladium graphitic carbonate catalyst, also the palladium carbon, activated carbon, and palladium charcoal also. So from this optimization table, you can see that the 1 and 2% of the palladium GCN and palladium OGCN nanocomposite shows better catalytic activity in comparison to PDC with 5 metal percent and PD charcoal also with 5 metal percent and more. So we can see that the catalyst is quite active and quite efficient for the reduction of nitro groups. And we can see that here potassium formate is used as a hydrogen source. So these are the other applications. We can see that different other substituted nitro groups were also hydrogenated to the amine products. Moving to the other applications, in addition to the nitro group reduction, we also hydrogenated various alkenes and imines can be seen from this table. Various alkenes and imines were hydrogenated by using this potassium formate as a hydrogen source in presence of this PDOGCN catalyst. The interesting thing we did here that we knew that this catalyst is active for reducing the nitro groups as well as the imine group. What we did, we designed a one-pot synthesis of this N-benzyl aniline using this nitrobenzene and benzaldehyde. And we can see that our catalyst is selective for the nitro group, not for the aldehyde groups. So in situ, it was reduced to the amine group, and this amine when react with benzaldehyde to form this imine. And now we can see that imine can also be reduced in situ to the amine. So forming this whole process, two-step process, three-step process in a single step, just by using nitrobenzene and benzaldehyde, we were able to get this N-benzyl-aniline product, which is a very important precursor for the various antihistamines, such as we can see that entazolines and etc. And finally, this work was recently published in ACS Omega. Thank you for your attention. I wish you all an energy efficient and sustainable research journey. And happy World Environment Day once again.
Thank you, Dr. Ashish, for your talk. So as we don't receive any questions, so we move on to our next speaker, Dr. Prabhat Agnihotri from IIT Ropar, and he will talk about the flexible adsorbent for energy harvesting. So Dr. Prabhat Agnihotri, please start your presentation.
Thank you, sir. So let me get the earlier speaker disconnect, or let me share now. So am I audible?
Yeah, you are.
And my slides are visible?
No, not yet.
Are they visible now?
No, not yet. So have you shared your presentation yet?
Yes, I have shared.
You have to share the screen. So
I have shared the screen.
It is not visible yet, actually.
Okay. Maybe I have shared the presentation to the community.
Have you sent it before, or you would like to send?
No, I have already sent it.
Okay, then wait for a minute.
What the minute is, Mr. Khai, what you can do, Mr. Khai, what you can consider doing is please instead of sharing the screen, first please exit sharing.
Yeah, I've exited now. Yeah.
Yeah. Now you reshare, but share the window, not the screen. So after you do share, scroll down, and then then just click on the window of your particular file.
I am this sharing this arrow. I have to push, right? The upward arrow.
The arrow once, then scroll down and open the window of your file. After you push the arrow, just scroll to the bottom of the page. You'll see different files over there.
Yeah.
Select the image of the file that you want to show.
Okay, that's what we have done. Is it? Are you able to see now?
Have you double clicked it? You need to double click it. It's not coming.
See anything.
No, it's not sharing so far. Dr. Bekul, could you find the file? You should be able to prepare this.
Your entire screen, application window. Okay.
Yeah, application window. Share application window, and then scroll down. Got it. It's coming now.
It's coming. Okay.
You have it. Thank you.
Okay. Thank you. Thank you for the help.
Thanks, Dr. Bekul.
Okay. So I can start now.
Yes, please.
Okay, so happy Environment Day, all of you. And this is Dr. Prabhat from IIT Ropar. So we are basically from mechanical engineering background. So I'll be talking more about how to make things which are easy to use, rather than not too much about synthesis, because we are not good at that. So we'll be looking for help in that aspect. So what this work is concerned is about the flexible adsorbent, which we call them FlexOr, for energy harvesting, which means through harnessing the solar energy. So as we know, the application that it is used in many areas like solar cells, cameras, and black paints, anti-glaring screen. So there are a lot of applications which are potential application for this kind of flexible absorber. And the question which we are looking to answer through this work is that if you look at most of the absorber, they actually work efficiently in visible range only, which means that the large portion of solar energy goes unutilized. And that is one of the reasons why the low efficiency of conventional solar cell, as one of the speaker from Massachusetts Institute has also shared about the low efficiency. So we think that one of the reasons for the lower efficiency is that we are not harnessing the entire spectrum. We are only focusing on the portion of the spectrum. So that is one thing. Can we absorb a better broadband wavelength? That is one question. Other question is these, like most of it based on the silicon solar cells. So they are basically rigid. So if you have a curvature surface or some non-planar geometry, these panels are difficult to mount. So for example, I want to mount these panels on the wing of an aircraft or some other or a roof on an automobile. So these things are very difficult to mount. If they are mounted, they are very, failure for like brittle failure during the use. So there are also a few questions about the rigidity. Third question was that when you look at the observer, then sun moves along on the daytime. So the efficiency of the observer also becomes the function of the position of the sun, which means the efficiency is a function of the incident angle of the beam. So can we do something about it? So there are three basic questions which we are looking to answer through this work. And we'll see. So this becomes the objective of this work. So we want to increase the wavelength, and we want to make it angle independent. We want to create impedance mismatch. We want to minimize that, and we want to make the this video is playing. We want to make it flexible. So if video is visible, this flexible absorber. Excuse me. Hello. Am I audible?
You are audible.
Okay. So these are the four things which we were looking at. So then we look back and see how the light interacts with the matter or any material or any object. So we have this incident ray, which falls on the object, and then part of the light is absorbed, part of reflected, and part of this is transmitted. So what the objective is, we want to minimize these two portion of the light, incident beam, and this we want to enhance. And if you look at the Amazon forest, this gives you an idea about, because it is a hierarchical structure, right? So there are a lot of multi-scattering features happens. So we want to increase the scattering inside the material to enhance the absorption of the light. And that's what we tried to do. So the first step was to make a flexible base. So to make a flexible base, what we did is we basically etched the silicon wafer. And once you etch the silicon wafer, you get a nice pattern, conical pattern. So one question which I will look at later, that how to optimize this pattern. So what is the right pattern to get? That is the first problem we had. Second problem is, now once we want to pour some flexible material, which is PDMS in this case, and then peel it off. So peeling off becomes a bit difficult, because when you peel it off, there is lots of chances of damage of this layer itself. So that is another problem which we need to optimize in this case. Once you do that, and then we get a texture kind of composite, and then which is basically the texture is seen here. So we'll go one by one through this. So first optimization is basically how to optimize this conical pillars. So that is what we did. We did extensive experimental optimization of this process by varying the etching time, etching temperature, and etching concentration of the solution. And then we finally zeroed it on one kind of solution, which is QH, and it is etched for 10 minutes. And that basically gives you, if you look at, this is the UV visible IR spectra of the silicon wafer etched for different parameters. So this is a P-type wafer, which is like a different combination we tried here, like I think around 8 or 10. So this brown one is the best one, and that basically happens for a cone angle. Top angle is 71 degree, and the base angle is about 54.5 degree, and that gives you the absorption of about 91.19%. So which is quite good. We have increased from about 60-70 to 91% just by etching the silicon wafer. We have done nothing. And this is basically, if you do a theoretical calculation, you will get the exactly same base angle which is required for a pillar to be an optimum absorber. So which we were able to get it experimentally, and this is the SEM image, and these are the FM micrographs of that. So once we get this optimum structure, we basically poured the sample PDMS composite. So the PDMS has basically a part of iron and zinc oxide and carbon nanotubes. Carbon nanotubes are basically used because they have a refractive index which is close to the air. So they basically help us to reduce the mismatch with the surface, air substrate surface. So once you do that, and the second thing is how much we should add. So that is the optimum filler loading. So what we did, we keep these all these concentration constant. So like if it is 3 weight percent, so 1% of Fe, 1% of ZNO, 1% of CNT. So all three are added in an equal measure. So then we varied the total concentration. So this is for pure PDMS, and we went up to 8 weight percent by varying 0.25, 0.51. So this is pure PDMS, which is able to absorb only less than 20%. And then we zoom in here. So what we see here, this is the green line, which basically is correspond to 1 weight percent of addition of all three fillers. So they combine. So basically, individual fillers are 0.3 weight percent, 0.3 and 0.3. So total is about 1 weight percent, and that gives you a maximum absorption about 96%. And if you look at the range, which is about 400 to 2000, and this is like broadband range. So efficiency drops suddenly a little bit after 800, but still it's quite high, around 95 or so. So that means the 1 weight percent is solution is enough. So what is the reason for that? Why it is 1%? If you increase, so if you are below 1 weight percent, the scattering is not enough. So that means the light is not being trapped efficiently inside the material. So that is when you move beyond 1 weight percent, what happens? These are the nanofillers. They form the agglomerates, and these agglomerates are basically not helping in the scattering of the light, and that's why they are not efficient. So the 1 weight percent is basically the optimum weight percent, where you have uniform dispersion of these fillers, and the scattering event is maximized in this case. So that is basically gives us a quite nice absorption in the whole broadband region. So now the thing is we have to combine this. So this and addition of these fillers will enhance the multi-scattering, and then on top of it, if you put the conical texturing on the surface, so this will be the combined effect of multiple scattering because of the fillers and because of the pillars. So this is what we did here, and if you look at this picture, so these are the earlier we have already seen. So these are the two which we should focus here. So this one is the untextured, and one is the textured composite. Textured is like slightly purple. So that basically texturing. So 96.5 is no texturing, which means we have a composite, and it is about 96 that we saw earlier. And once you do texturing, then it goes improves by about 3% again. So it goes more than 99% in the whole UV visible IR region. So basically, it's a combined effect of texturing and filler addition, which is schematically explained here. So once light falls on this pure PDMS, so it is basically most of the thing is transmitted. So nothing happens here. Once you add these untextured, these fillers and the untextured composite PDMS, it does a lot of scattering, and the beam loses its energy, and it also gets heat up that I will not talk about here. But it helps you to improve about absorption by 96%, and then you do a texturing at the top surface that basically takes you up to the 99% in the whole range UV visible in IR, which means that it is able to absorb the light in a broader spectrum as compared to visible only. Now, because of this flexible nature, it can be mounted on any substrate. But what is the adhesion strength? Suppose if I mount it, or there are different types of surfaces it will encounter light. For example, it can be mounted on the metal, can it be mounted on the plastics, or can it be mounted on the glass? So then we did a peel-off study, so just to see how the adhesion of these flex orb is. So this is a standard test which is called peel-off test. So what you stick a layer, and then you apply a force. So this is like a mode 1 loading in a typical fracture mechanics concept, and then it will try to delaminate. So this is the delamination which happens here. Now you do it with 3 different surfaces, which is metal, plastic, and glass. And then we see what is the strength of the bond between the flex orb and the underlying surfaces. So it takes a lot of force. You see about 2 Newton, about 4 Newton for metal, and then about 2 Newton is for plastic, and the glass is a little bit lower because of the its surface finish was quite good. So the adhesion strength was not that high, but still this force is quite good, and it can sustain environmental or these surface conditions pretty well. So these are the numbers in terms of comparison. So if the maximum peel-off force, of course, it is better with the metal, but plastic is also fine. Glass is slightly lower, but if you can rough the surface to some emery paper or something, then it will again improve. Similarly, the peel strength also is higher with the metal and plastics in glass. So that means that it can be mounted with a sufficiently high adhesive strength on any kind of surfaces, which is like three we have studied: plastic, metal, and glass. Then we did another test, which is again the measure of how the bonding is called lap shear test. So here basically this is the point lap joint which you make, and then you apply a force on this joint and this side, and then basically it will shear from here. And then again you see that it shows a better strength with the glass than the metal and then the plastic. So which means that it can sustain the service conditions pretty well. Other environmental degradation is another critical problem with these surfaces, as pointed out by other speaker as well. So we basically try to see how well it is helpful in that, because this texturing will induce the hydrophobicity in the sample, and that's what we basically found out by contact angle analysis. So pure bed is about 108 degree, and then it's go to about 138 degree, which means it can resist the degradation because of the moisture. So if rain falls on it, it will not absorb the water and it will repel the water, and so that the durability of the absorber will be higher. So all these studies are published in Advanced Material Technology, and there are more things, but I will not, because time is running out. So these are the take-home messages. So we are able to develop a flexible absorber which can basically absorb the light in the broader spectrum spectrum of UV visible in NIR with a capacity of more than 99%, with the addition of 1 per of filler and some texturing at the surface by, and then it can be mounted on any type of substrate like metal, plastic, and glass. And it is we are testing it performance in a real life solution for solar heaters. So we are putting in the form of a paint, and then we are trying to see whether it is actually enhances the efficiency of the solar heaters or not. But for other solar cell kind of thing, I'm not the right person to do. So maybe if somebody is interested, I can talk to him, and we can try it out in other solar energy devices. How does it perform? Okay, so I'll stop here, and I'll not take much of your time. Okay, thank you for your attention.
Thank you very much. Thank you very much, sir. And now, I think if anybody has any questions, they can ask questions. So there are no questions. We can just move forward with the oral presentations of two of our participants. Firstly, I'll be inviting Ms. Ruchi Srivastav to give her presentation. Ms. Ruchi Srivastav, please come on your screen. Share your screen and unmute yourself. I think the issues has been resolved now.
Hello, good evening, everyone. Am I audible?
Yeah, you're audible. Yeah, you're audible. You can just start by delivering the main content of your presentation.
Right. Thank you, ma'am. Thank you so much. Today, I'm going to present my work on green corrosion inhibitors, eco-friendly corrosion inhibitors, and I'll run through my through the PPTs as time is I'm falling short of time, I think. So talking about eco-friendly corrosion inhibitors. Today, as we all know, that mild steel is one of the most important basic material with excellent structural and mechanical strength, and hence it is extensively used in industries and as high quality engineering material. However, this mild steel tends to interact with the environment and it gets corroded very easily, especially in acidic solutions. As we know, in industries, acidic solutions, especially HCl, is used in the industries for various metallurgical purposes, and in petrochemical industries for alkylation and polymerization processes. So I'll be studying corrosion inhibition on mild steel in acidic medium, in HCl medium. These corrosion inhibitors, the purpose of my study is basically to maintain the soundness, the integrity of the structure, and to get a corrosion-free metal surface. And as we all know, corroded surfaces, they pose a great threat to human and environmental health, as a lot of chemicals, they escape from the corroded equipment. So controlling corrosion now becomes very essential, such as to reduce the risks, the health risks which they are posing. Now, various methods of corrosion control are already in use, such as various protective coatings. Anodic and cathodic areas are protected differently from corrosion. The type of material selected, design of the material is selected according to, is seen according to, which corrodes less. Then we are using a lot of corrosion inhibitors in the market also. Actually, the purpose of this study was to introduce some green corrosion inhibitors, such that these corrosion inhibitors which are being presently used and are toxic, so that toxicity could be reduced, and some green corrosion inhibitors are to be given to the are the need of the market right now. So corrosion inhibitors, the corrosion inhibitor which I am choosing is a very common plant found in Mizoram, Northeast. I've been staying there for a long time, and I found this plant which we call nohari in Mizoram. It is a plant which is used as a flavoring agent. It is a very good it is a very good anti-inflammation plant, used for anti-inflammation. And a very common disease there is nohari, found especially in children, which is a combination of fever, cholera, skin diseases and inflammation. And this plant extract is put on the inflamed part of the skin, and the disease, they vanish. I've seen this. So I thought of starting this work from Mizoram only by using that plant, and it is known as Eschscholzia communis inflorescens, ECI. I'll be referring it in this presentation. Now, this was used as a corrosion inhibitor on mild steel, which is almost used in all the industries and petrochemical pipelines everywhere. And this mild steel, it corrodes very easily. So I'm using, it corrodes easily in HCl solutions. And so I'm using this green inhibitor, my plant extract, ECI plant extract, as a corrosion inhibitor on mild steel in HCl solution. Now, the very extensive experimental studies were carried on to prove the inhibition of this plant extract on mild steel. We checked for the corrosion inhibition through weight loss methods, potentiodynamic polarization, electrochemical impedance spectroscopy was studied. We studied the temperature effects. I'm quickly showing the method, the analysis which we have done. First of all, the identification of the phytochemical constituents in the plant extract was done using GCMS. These are just a few of the constituents which were found out of maybe around 20 to 22 constituents. I'm naming a few, which contains beta carotene, retinoic acid, and the basic chemical structure is shown here of retinol acetate and some other constituents which are found in the plant extract. Now, after performing the GCMS, we checked for corrosion inhibition effects by taking the weight of mild steel dipped in HCl before application of the inhibitor and after application of the inhibitor, and we calculated the corrosion rate. We studied the inhibitor efficiency and through extensive studies, and calculated the corrosion rate. We studied and we plotted the concentration graph, and we found it followed Langmuir absorption, and the weight loss measurements which we did was tabulated, and it clearly indicates that with increase in the concentration of the inhibitor on the mild steel surface, like 0.1 to 0.3 to 0.5 gram per liter, it is seen that the corrosion rate decreases significantly from 3.17 to 0.51 milligram per centimeter square, and the inhibitor efficiency increased a lot. With the increase in concentration of the inhibitor on the metal surface, the inhibitor efficiency increased a lot. Of the inhibitor. Hello.
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 Yes, sir. Yes, I'll continue. In the table, we can easily find that with the increase in the concentration of the inhibitor, the absorption.
Your presentation is not visible.
The screen is not.
Now it is. Now it is.
Okay. The table in the table we can easily see that the corrosion rate decreases with increase in the concentration of the inhibitor. We studied temperature effects also, and we found that with increase in temperature, the corrosion rate with increase in temperature, the rate of corrosion decreased significantly. And further, what we did was we plotted our concentration and we found that they followed Langmuir absorption isotherms, and these Langmuir absorption isotherms, through these isotherms, we could easily find out that the mechanism which the inhibitors follow was physisorption rather than chemisorption at lower temperature. And finally, we calculated also the thermodynamic activation parameters, and we found out that the activation energy, with increase in the activation energy in the presence of the inhibitor, we found that physical absorption of the inhibitor molecules was happening on the mild surface. The concentration was dependent upon the inhibitors, and there was a kind of physical barrier between the mild steel and the surface solution interface. Further, we calculated we also checked the potential dynamic polarization and the electrochemical impedance spectroscopy. We plotted the Tafel plot and the Nyquist plots, and easily we could from the Tafel plots we could derive that the inhibition effect that the plot showed that as the inhibitor concentration increased, more absorption was on the cathodic area. So the inhibitors were were behaving as cathodic inhibitors rather than anodic inhibitors. And from the EIS spectroscopy, from the Nyquist plot in the next figure, we could deduce from these Nyquist plot that inhibition mechanism does not depend upon concentration, as the semicircular path which the blank solution was following was similar to what the mild steel was following with different coatings of the inhibitor. They followed the same semicircular path. So we could find out that inhibition mechanism that did not depend upon the concentration, but the increase in the diameter of the impedance plot with the increase in concentration show that the absorption of the plant extract increased with the concentration of the extract. The absorption increased, but the mechanism did not depend upon concentration. Rather, the mechanism was depending upon charge transfer processes. In the last, we also checked for the SEM images, and we found the first image is showing the mild steel without any the polished surface of the mild steel. The second one is with when the mild steel was dipped in HCl solution, and the third the SEM image, it shows the when mild steel was dipped in HCl solution along with the coating of our plant extract, and the surface shows uniformity from the second figure, which shows a lot of corrosion of mild steel in HCl medium. So this from our study, which we concluded that the application of corrosion inhibitors using natural products, ECI in our case, using natural products, inhibited the corrosion rate to a great extent, and would be much favorable for the industries, as they are green inhibitors rather than toxic effects which the synthetic inorganic inhibitors are being posing a threat to the industry. Thank you.
Thank you very much, Ms. Ruchi Srivastava, for such a nice presentation.
Thank you, ma'am.
So we have some questions. The first question is from Dr. Sudeep Ganguly. Can you please tell which standard have you used, which ASTM standard have you used to measure the corrosion rate?
Yes, ma'am.
Can you please tell us which standard have you used to measure the corrosion rate? Which ASTM standard, or is there any standard method to measure the corrosion rate?
Ma'am, I'm not able to get the question. What?
So the
thickness,
question
is he asking that about the thickness?
So he's asking about the standard method which you have used to measure the corrosion rate. Or is there specifically some derived equation?
Yeah, there are a lot of derived equations. We calculated the weight loss by the weight loss method by potential dynamic polarization. Actually, it was limited to 4 or 5 slides, so I did not show all the tables and the graphs. The potential dynamic polarization was studied, the electrochemical impedance spectroscopy was studied, and inhibition efficiency was clearly proved that the plant extract showed great inhibition efficiency on mild steel when in HCl solution.
Okay. So basically you're saying that the equations were just derived equations, okay, right? And there were some other parameters that you calculated and that you are not showing in this presentation, right?
Yeah. We calculate with theoretical calculations also we did, but I did not show it. Trying to limit the number of slides, I did not show. DFT we also did. We also performed a DFT on the molecules.
Okay.
DFT on the optimized structures.
Okay. So you have taken iron as a material, as a surface for your study for mice.
Madam Neha, in the time constraints, can we have the discussion offline maybe?
Yeah, right, sir. So I invite the next oral presenter, Miss Srija, for her presentation, which was left in the earlier theme. So please, Miss Srija.
Okay. Hello, is it visible? Hello? Is it visible? Hello?
Please share your screen.
Now is it visible, ma'am?
Yeah, it's visible. Please start.
Okay, thank you. Hello, good evening, everyone. Introducing myself, I am Sreeja, Research Scholar, National Institute of Technology, Calicut, Department of Chemical Engineering. Before starting, I wish you a happy World Environment Day. So today, nowadays, we are facing the whole world is facing in a situation of lockdown, right? So because of the outbreak of coronavirus, it caused a disease known as it developed a difficulty. We are now facing in a difficulty to control the spread of COVID-19. This has spread, as we all know, this has spread through the droplets while sneezing or coughing, or through the close contact known as primary contact. Due to the spike-like protein present in the coronavirus, it has higher infecting capacity than the previously discovered coronavirus. This coronavirus outbreak had happened earlier also, but due to the spike-like protein and all, these are having much more. It's healthier to infect human beings. So the virus mainly attacks to the ACE2 receptors, angiotensin conversion enzyme, and enters into the human body, thereby replicates its genetic material RNA, causing severe breathing difficulty. Excuse me, I will present from the causing serious difficulty problem in breathing. In severe cases, it may cause pneumonia, etc. So to prevent the transmission of disease, people we have to keep social distancing is the main source of prevention of such kind of disease. Now this presentation deals with the development of a mask, antivirus mask using polymer composite, which was synthesized using a polymer composite, which makes the people to travel confidently outside. I mean, travel or work in an environment. This is the overview of presentation. It deals with introduction, then the classification of face mask, principle and description, then the parts of face mask, advantages of reusable face mask, and conclusion followed by references. Going on for the introduction part, as I mentioned earlier, SARS coronavirus 2 are spherical and have spike-like protein which binds to the binds to the human being. The mechanism of action is it binds to the ACE2 receptors. On the right hand side, we can see the transmission electron microscope images that shows SARS coronavirus. The symptoms include the shortness of breath or difficulty breathing, muscle aches, chills, or sore throat. In severe cases, it may cause chronic liver or kidney diseases. Face mask. Face mask is an interference device between the patient's upper way and the breathing system. It allows the gas administration to the patient from breathing system. Now, we can classify face mask into different types. N95. It's the efficient way of using the face mask. Now, it is followed in the hospitals and all. Now, based on function, it can be classified as comfort mask, surgical respirators, particular respirators. Based on usage, we can classify it as disposable face mask and reusable face mask. Our presentation mainly deals with the reusable face mask. Now, the principle and description. In this face mask, the principle is like this. In virus sterilization filter, used in face mask, air is passed through the galvanic laminates, which has different electromotive forces. As the passed air gets contacted with the two materials having different ionization tendencies, sterilization activity occurs then. The virus sterilization filter consists of the planar-shaped galvanic material with multiple nano-sized pores for air passage, which is sterilized through an electromotive force. The description that the face mask can be made up of black rubber, clear plastic or elastomeric material, or the combination. We can use the combination of these to make the face shield. That's the outer part covering of the face mask. This is the main part of this. It consists of a body and an orifice and a rim and the retaining hooks. This body shell, the materials we can use it like this. The body shell can be made from the polyolefin resins or the polysulfone resins. It contains a galvanic material made of carbon and the second galvanic material coated on one side with brass. Woven body is made of a base layer which is fibrous in structure, consisting of a normal woven fabric or non-fabric and a nano fabric material. It has a particle blocking range of 80% and a porosity of more than 30% in it. The nanofiber membrane can be selected from a polyamide resin or polyacrylate or polysulfonide resin. The base layer is used to cover the front and the rear part of virus sterilization filter to filter large foreign particles. The fiber base made up of paper, glass, silica, etc. So the nanofiber membrane layer is designed to filter foreign particles in air through substrate layer and has a number averager of 1000 nanometer. This nanofiber can be designed in the range of 10 nanometer. Body portion of mask is made of galvanic laminated portion and fabric made fabric by a body surrounding it. To consider the reusability, the reusable masks, why we are going for the reusable masks? Because it is economically viable. So considering the reusability, the outer portion of the mask is to cover the nose and the mouth of the mask gel is thermoformed of cross-link closed cell foam sheet which is impermeable to air. Also the materials having good shape, retention and elasticity. Why we want to go for reusable mask? Because it is economically viable and we can only we need to change the filter inside the mask. So we can reuse it again, and as well as nowadays we can see that the mask once we are using, it is discarded into the environment, causing severe issues to the whole the people and all. Not only for people, animals surrounding there. So we have to be very much care that before we are discarding to the environment, we have to take it in proper treatment. We have to discard it safely. So if we are using a reusable mask, means we can only change the filters present in it, so that it is economically viable also. It costs about 2 to 3 rupees for a single filter. Rather than we are spending 30, 40 rupees for a single mask, we can use the reusable mask and change the filters itself. So virus particles or any other foreign particles can be sterilized like this. What is the need for that? We know that the coronavirus, the outer membrane is made up of lipid layer. When we are spraying or covering or when we are coated this outer part of the mask with the detergent or antivirus material, antivirus agent, this when the virus particles hit onto it, it gets degraded because detergent as in hospitals and in doctors are suggesting us to use frequently wash your hands with the detergent, the soap. Why? Because the soap have the tendency to degrade the outer layer of the bacteria or the microorganisms, viruses also, thereby degrading the virus particles. So using these kind of the reusable mask, it's highly safety for the health workers, medical professionals who are handling the virus infected patients. Disposal of used, as mentioned earlier, disposal of used face masks without proper treatment can be avoided while using this kind of the reusable face mask. It's economically favorable too. Now, going on for the conclusion part, it is profitable and a needful product, especially in the current situation. People now are facing a difficulty due to the spread outbreak of these diseases. Investing and diversifying in the present situation. Usually in industries, in our college also, we have planned and developed a 3-dimensional face mask covering the whole face. Covering the whole face with a transparent sheet, and especially the mouth and the nose is covered with a 3-dimensional face mask. Which has a outer pressure releasing air vent. Air gases are being passed on through these small vents, and the inlet air is being sterilized with the help of the face mask. So it has a high market potential in the current situation, focusing in areas such as industry, tourist mass production. It is now, nowadays, normally everywhere, we are facing a shortage of mask. So it is now a needy product for the whole society. So sterilization, here the sterilization principle is applied here, which implement a high safety, especially for the health workers. economically viable and affordable, it increased the efficiency of oxygen intake for breathing compared to the normally used face mask. In normally used face mask, we feel difficulty in getting in breathing and all because the air limit is very short. I mean very short amount. So if this has a small vents for the passage of the air, which increase the efficiency of oxygen intake, thereby increasing our breathing efficiency. So that same principle can also be used to manufacture kiosk in our Kerala government have provided a kiosk facility that can be synthesized also using this kind of the principle. The same principle can be applied here. Two galvanic material with different capacity can the electromotive forces between them will sterilize the virus particles, thereby which can be installed in the hospitals to collect samples from the infected patients. This it contains two galvanic material made of the carbon fiber and the second galvanic material coated on the one side with the brass. So a different ionization tendencies occur between the two galvanic materials that between them a electromotive forces develop and thereby sterilizes the virus particles. This product we are upgrading to some more level. Actually, it is under development. One of the products we have implemented in our college itself. Now we are upgrading to synthesize it in a more efficient way because testing and all should be conducted in a hospital, whether it is efficiently working out or not. So we are going on with this. By 2 or 3 months, we will try to develop it and increase in and improve it. Improve it. At least we are planning it to implement to in the whole state itself by within 2 or 3 months. And these are my references. And thank you, Anand, thank you for your kind attention.
Thank you very much, Ms. Srija, for such a nice presentation on the topic for development of mask, antivirus mask, the recent topic going on. So, thank you very much for contribution. And before moving to the valedictory session, whose chief guest is Dr. Rajendra Singh, who is also known as Waterman of India. Right now he will be joining us after 4 or 5 minutes, and so by that time we are really happy to share with you that the support that is given by our sponsors by sharing this video with you.
कंपाइल कर सकते हो थीम हाँ मैं फाइल्स भेज दूँ थीम डालना ये थीम 1 का की पॉइंट है ठीक है थीम 2 का अभी मैं थीम 2 का भेज रही हूँ थीम 5 का आ गया ना मेरा भी 5 हो गया ठीक है 5 हो गया हम किसके अकॉर्डिंग करते हैं
व्यवस्थाएं शामिल हो गई, बल्कि अंत तो समाजवादी विचारधारा उसमें ज्यादा आगे निकल गई और उसका लालच तो इतना ज्यादा बढ़ गया कि फिर तो उन्हें वायरस से भी डर नहीं लगा। और ये जो व्यवस्था है, ये व्यवस्था एक तरह से चरमरा गई। इस व्यवस्था में हमने जो ग्लोबल इकोनॉमिक नेट है उसको तो बहुत स्ट्रॉन्ग किया, लेकिन हमारा जो सिक्योरिटी एक्ट है, जिसको भारत के लोग शुभ कहते हैं, जिसको भारत के लोग सनातन कहते हैं, जिसको भारत के लोग सस्टेनेबल कहते हैं, ये जो वर्ड है ये हमें ये बताते हैं कि हम इस नेचर में यदि हमारा लालच ना बढ़े तो ये नेचर हम सबकी जरूरत पूरी कर सकती है, और जरूरत पूरी करके किसी की तनिक भी इसमें किसी की हानि नहीं होगी। सब इस किसी का क्षय नहीं होगा, किसी का बिगाड़ नहीं होगा, सब इस काम में बराबर आगे बढ़ते जाएंगे और प्रकृति में भी वृद्धि होगी। लेकिन जिसको हम डेवलपमेंट कहते हैं, जिसको हम मॉडर्न एजुकेशन कहते हैं, मॉडर्न एजुकेशन ने और डेवलपमेंट ने जो रास्ता पकड़ा, उसमें हमारी जो इंडिजिनस नॉलेज सिस्टम है और इंडियन विजडम है उसका डिस्प्लेसमेंट हुआ। और एक तरह से जो हमारी एजुकेशन में हमें टेक्नोलॉजी और इंजीनियरिंग सिखाई गई, उसमें हमें मैक्सिमम यूज ऑफ नेचुरल रिसोर्स में एक्सट्रैक्शन और एक्सप्लॉयटेशन की टेक्नोलॉजी और इंजीनियरिंग हम लोग पढ़ने लगे, और फिर हम भूल गए कि धरती के पेट में कितना पानी है, कितना पानी हमें निकालना चाहिए, कितना नहीं निकालना चाहिए। यदि हम धरती के पेट से पीने के लिए पानी निकाल रहे हैं तो उसमें वापस भी डालना है। तो हम एक तरह से डिस्चार्ज को हमने बहुत बढ़ाया और रिचार्ज हमारा छूट गया, हम रिचार्ज को भूल गए। इसलिए इस पर्यावरण को यदि हम ठीक करना चाहते हैं तो डिस्चार्ज और रिचार्ज का संतुलन बनाए बिना ना हमारी बायोडायवर्सिटी बच सकती, ना हमारे इकोसिस्टम बच सकते, ना हमारी क्लाइमेट सिक्योरिटी हो सकती, ना फूड सिक्योरिटी हो सकती, ना वाटर सिक्योरिटी हो सकती। यदि हम सिक्योरिटी इंश्योर करना चाहते हैं और सिक्योरिटी का अर्थ समझना चाहते हैं तो भारत के बिजनेस में, भारत की इंडस्ट्री में दो शब्द थे, एक था लाभ और दूसरा था सुख। सुख के बिना भारत के बिजनेस में लाभ की कल्पना नहीं थी। ये जो सुख था ये सिक्योरिटी था, ये हमारी सबकी कॉमन फ्यूचर की सिक्योरिटी था, क्लाइमेट की सिक्योरिटी था। लेकिन अब हमने सुख को भुला दिया और लाभ और लालच प्रबल हो गया। और जो कुछ बड़े अच्छे लोग हैं, साइंटिस्ट हैं, जिनके मन में इस कॉमन फ्यूचर की चिंता है, वो उदासीन हो गए। उन्होंने बोलना बंद कर दिया। वो कहने लगे कि भाई जब ये लालची लोग लगे हैं तो ये मेरे कहने से नहीं रुकेंगे। तो एक तरफ हमारा लालच, दूसरी तरफ लाभ की प्रतियोगिता और तीसरी तरफ उदासीनता। इसके कारण हमारा पर्यावरण बिगड़ा है। हमें यदि इस पर्यावरण को सुधारना है तो देखिए, आप जैसी यूनिवर्सिटी, आप जैसा वैज्ञानिकों का बड़ा योग्य समूह अपने फ्यूचर को सुरक्षित करने के लिए हमारी जो क्लाइमेट सिक्योरिटी है उसको इंश्योर कराने में क्लाइमेट चेंज अडेप्टेशन और नेचर की अडेप्टेशन, नेचर की रेस्पेक्ट हमारे व्यवहार में लाने की जरूरत है। आज हमारे व्यवहार से प्रकृति का सम्मान घट गया है और प्रकृति का सम्मान घटने के कारण हम लोग लोभ लालच में पड़ गए हैं। मित्रों, यदि हम लोभ लालच से ऊपर उठकर प्रकृति को संभालने की कोशिश करें तो प्रकृति हम सब की जरूरत पूरी करने में आज भी सक्षम है, जबकि दुनिया ने प्रकृति को बहुत बिगाड़ दिया है। बहुत सारे देशों का लालच तो हमसे कई गुना आगे है। दोस्तों, भारत दुनिया का टीचर था, ग्लोबल टीचर था, भारत दुनिया का गुरु था। भारत दुनिया का गुरु तभी तक था जब तक वो मानव, पंच महाभूतों से निर्मित मानव और पंच महाभूतों से निर्मित ये ब्रह्मांड, ये प्लेनेट, इस सबको बराबरी से देखता था और दोनों का बराबर हक था, दोनों का बराबर रिश्ता था। ये जो भारत का इंडिजिनस नॉलेज सिस्टम था और ये जो भारत की इंडियन विजडम थी, वो लंबे समय तक भारत को दुनिया का गुरु बना के रखे हुई थी। आज हमारी वो विजडम, आज हमारा वो नॉलेज सिस्टम हमसे छूट गया है। इसलिए हम उस नॉलेज सिस्टम को दोबारा से रिवाइव करने की कोशिश करें तो भारतीय आस्था पर्यावरण की रक्षा के लिए हमें आगे बढ़ाएगी और हम दुनिया के फिर से गुरु बनेंगे। मैं आपके इस पेट्रोलियम यूनिवर्सिटी को, संस्थान को, आपके इस संस्थान को कॉन्ग्रेचुलेट करना चाहता हूँ, बधाई देना चाहता हूँ, आपके डायरेक्टर को, आपके चेयरमैन को, आप सबको, कि आपने इस विश्व पर्यावरण दिवस पर कुछ नया रास्ता खोजने के लिए, और वो नया रास्ता है क्लाइमेट चेंज अडेप्टेशन का। वो नया रास्ता है हमारी नेचुरल रूरल इकोनॉमी को डिसेंट्रलाइज्ड वे में स्ट्रॉन्ग करने का। ये जो सेंट्रलाइज्ड प्रॉफिट इकोनॉमी है उसको रोककर हम नेचुरल डिसेंट्रलाइज्ड इकोनॉमी को बढ़ावा दें। उससे हमारे देश का आत्म स्वावलंबन बढ़ेगा, भारत गौरवशाली होगा और भारत दुनिया को सिखाने के लायक बनेगा। मैं आज के इस वैलिडिटी सेशन में आप सबको बधाई देते हुए इतना ही कहना चाहता हूँ कि अभी भी वक्त है हमारी समाज और हमारी सरकार दोनों मिलकर इस प्रकृति को ठीक से समझें। दोस्तों, आप जानते हैं कि कोविड-19 के बाद एक बड़ा चेंज आया है। कोविड-19 ने, मैं पिछले 37 सालों से और कभी कहूं तो 40 सालों से ये कह रहा था कि इस नेचर में अपने आप पुनर्जीवित करने की क्षमता है यदि हम हमारा लालच थोड़ा रोक दें। लेकिन किसी ने नहीं सुना। कोविड-19 ने ये प्रूव कर दिया, लॉकडाउन ने ये प्रूव कर दिया कि जो गंगा हजारों करोड़ खर्च करने पर ठीक नहीं हुई, जिसको हम माँ कहते थे, माँ हमारा मैला धोने का काम करती है, मैला ढोने का काम नहीं करती, और हमने अपनी माँ को मैला ढोने के काम में लगा दिया। तो जब माँ को हमने अपनी मैला ढोने के काम में लगाया तो माँ आईसीयू में भर्ती हो गई और माँ के बस की माँ अपनी ताकत को भूल गई। दोस्तों, लॉकडाउन ने माँ की ताकत दोबारा से खड़ी की। जब हमारे गंदे नाले और जब हमारे औद्योगिक गंदगी गंगा में जानी बंद हुई तो हम पानीदार बन गए। हमारी गंगा फिर से अविरल निर्मल होकर बहने लगी। हमें बस आज इतना ही कहना है कि कोविड-19 ने गांवों के गणराज्य भारत को स्वावलंबन, स्वाभिमान और स्वराज्य के रास्ते पर लाने का मौका दिया है, क्योंकि अब गांव के लोग शहरों से वापस आ रहे हैं। जिस प्लान के कारण हमारे अर्बन लैंडस्केप डेंजरस हो गया था और अर्बन फ्यूचर बिगड़ रहा था, अब वो अर्बन फ्यूचर ठीक हो सकता है जब गांव के लोग अपने गांव में जाकर अपनी खेती करेंगे, पानी का काम करेंगे, मिट्टी बचाएंगे, पर्यावरण बचाएंगे, प्रकृति की रक्षा करेंगे और हमारी सरकार उस काम में मदद करे। हम सब मिलकर भारत को एक बार फिर पानीदार बनाएं, भारत को जलवायु परिवर्तन की सुरक्षा प्रदान करें। हम सब मिलकर पर्यावरणीय रक्षा के लिए भारतीय आस्था को और भारतीय ज्ञान को जगाएं। जय हिंद।
बहुत बहुत धन्यवाद आपका डॉक्टर राजेंद्र सिंह जी। आपने जो बातें बताई वो तो हम सबके दिल के बहुत करीब होनी चाहिए थी, पर हम उनसे भूल गए थे। तो आशा करते हैं कि अब शायद हम उस पर अमल करने की कोशिश करेंगे। तो आपको बहुत बहुत धन्यवाद, और अब मैं नेहा जी से कहता हूँ कि आगे का कार्यक्रम करें।
सबको धन्यवाद। जय हिंद।
जय हिंद।
Thank you very much, sir. Thank you very much, Chief Guest, for addressing. And moving forward now, I request Dr. Pranav Das to summarize this event and continue forward validation session.
Thank you, Neha. Good afternoon to all of the participants. So we are coming toward the closure of the event. So I will just briefly summarize without taking much time because of the time constraints. So our student convener Neha Sharma, she actually introduced the event to all of us, followed by welcome address by our director IIP, Dr. Anjan Ray. Thank you, sir. Followed by this, our chief guest, Dr. R.K. Malhotra, Director General of Federation of Indian Petroleum Industry, enlighten us on energy transition in post-COVID era. So he emphasized on the global temperature, the way it was changing in the last few decades. So previous target was 2 degrees centigrade. Now it has changed down to 1.5 degrees centigrade. And the final target set by IPCC, is the Intergovernmental Panel for Climate Change, is set as to make the carbon neutral by 2050. So accordingly, all the happenings will take place across the globe. So he emphasized on how COVID-19 impacted the environment. Skies have become, skies became so clear, and this year's contribution to temperature rise will be minimum in as compared to the last few decades, year-wise. So he also emphasized that 2/3 of the oil consumption gone down at this point of time as compared to the earlier year, and he expect during this year, 10 to 20% fuel consumption will reduce as compared to the last year. So digitalization is the way forward of life, as he mentioned. So he also mentioned that renewable energy will play a crucial role in the future, such as hydrogen. So he emphasized on new technologies, like hybrid technology. So he emphasized on hybrid technologies instead of EVs, because for EVs in a country like us, we have power plants which burns coal, and we produce CO2 in a remote place, and that electricity is actually used for running the batteries. So it makes it is not that innovative thing. Instead, we should focus on hybrid technology that IOCL is already in the way. They are pushing hard for this hydrogen as a future fuel. So with this, he concluded his talk, and after that we had our guest of honor today for this entire session. So he is Padma Shri. We are Padma Shri awardee and professor of IIT Madras, Professor T. Pradeep. He began his talk with the quote that the millennials are seeing the blue skies across the globe for the first time. Yes, sir, we agree that for the first time we are seeing this such a beautiful sky because of this, COVID. And he emphasized on the importance of nanomaterial in water harvesting, and he also said that 83% of the freshwater species declined since last 50 years because of the pollution. So after that, we had 5 technical sessions. So I'm not going into the detailed technical sessions because of the time constraint. So altogether, we had 5 keynote speakers, 10 guest speakers, 7 oral presentations, 10 poster presentations. And 300 participants and viewers actually viewed this program across all the platforms such as Facebook Live, YouTube, and this Microsoft Team platform. So after that, with this, technical sessions were closed, and after that, we just heard about the our guest of honor for this valedictory address by Dr. Rajendra Singh, the Waterman of India. He emphasized on the nature and environment, and he firmly believes that we can revive the environment that we had in early days. And the way the migration is taking place from cities to the villages, that is another opportunity to revive our rural economy, provided that all the facilities and the infrastructure is provided to the rural people. With that, I thank our chief guest, Dr. R.K. Malhotra, DG of Federation of Indian Petroleum Industry, for his talk. I thank to guest of honor, Padma Shri Professor T. Pradeep, for his participation. I thank all the speakers and participants. This time we reached out to many international delegates, and we are thankful that this event was graced by their participation and wonderful talks in many of the sessions. Now, on behalf of organizing committee, I thank to Dr. Anjan Dey, Director IIP, for guiding and mentoring us from day one when we kickstart the activities of the program sometime in October. I thank all the Sefco team members for your wholehearted participation and involvement. I thank all my colleagues for extending your support in organizing this prestigious event. I also thank our sponsors, namely Swisslock, Mark, CSIR, ACRC, Adarsh Enterprises, Blaze Analyticals. Thank you all of these sponsors for extending your financial support, sir. We look forward to all of you in future events also. I thank all media personnels for covering this event. Now I request Dr. Bipul Sarkar to announce the best poster and oral presentation awards. Immediately after that, once he announces this, Mr. Amar Jain, Chief Scientist of CSIR-IIP, will be making his closing notes of this event. Now I hand over this virtual platform to Bipul Sarkar. Thank you.
Thank you, Dr. Pranav. On behalf of Sefco 2020, we thank all of our speakers, participants in all capacities for sharing their views and works in that virtual platform. Based on the evaluation done by our evaluator, the best oral presentation goes to Dr. Prabhat K. Agnihotri for his talk on flexible adsorbent for energy harvesting. For the poster presentation, we have Anjali Kumari Garg for his poster, the synthesis and application of waste pills drive photoactive carbon dots, and we have a joint first poster awards for Mr. Arka Prabhu Giri. So, resourcing for arene-based porous organic polymers for CO2 fixation and micropollutant removal from water. We thank both of three for enlightening us with their works, and I call Neha on stage to start.
Thank you very much, Dr. Bipul. And now I invite Dr. Shri Amar Kumar Jain for his closing address to this event. Mr. Amar Kumar Jain, please.
Thank you, Neha. I think this has been a fascinating event. I was little apprehensive that due to COVID-19, we are going the virtual way and how it will come out. But it is really wonderful. You people have done a great job. So I congratulate all of you and the presenters, the listeners and everybody, because it has been a great experience and we have not even learned how to do the virtual event successfully, but also in a way to learn that how to live in such a difficult time and how to perform in even better in a difficult time. So I give my best wishes to all of you and not to take much of the time because it's already 6:30 and I suppose everybody has to reach home by 7. After that, the city is closed. So I again wish all the best for all of you and declare the event closed. Thank you very much.
Thank you.
Thank you very much. I think with this address of yours, now we are at the end of the program, and we are very happy for your for believing in us that we could be able to conduct this virtual event, and we look forward to the participation of all the participants in our next events too. Thank you very much, everyone, and congratulations once again to the poster and the oral winners.
Thank you, Neha. So let's hope to meet again next year. Thank you.
Sure. Thank you.